Here's another question on special relativity where we have a ship that's travelling at about 92% the speed of light and we have to solve some problems with it. So here we go. So there's a whole series of questions here. So here's the first one. Spacecraft is measured as 35 meters long by someone who's on the spacecraft. And what you have to do is, first of all, a bit of show understanding that you know the differences between Galilean and special relativity. And then if an observer on Earth sees the spacecraft, you have to figure out what length they see it as. So it should be fairly obvious that that's going to be length contraction. After that, we've got a rocket traveling in the opposite direction, and it is also moving at relativistic velocities. It's moving at 0.75 c. Now you've got a couple of questions related to some questionable velocities there, and you need to calculate what its actual velocity is next. Then decide according to your understanding of physics which one is likely to be correct. So pause the video, see if you can solve it, or here are the solutions. So firstly, Galilean and special relativity differ in the fact that in both cases, the rules of physics, the laws of physics are the same in all reference frames. It's when you're comparing frames that things become a little bit different. Time is not absolute, so something moving faster will experience time slowed down. Fast-moving objects experience time slower. They also shrink relative to observers. So yeah, time is not absolute in all reference frames. And also the speed of light is constant regardless of what speed you're moving at. So this goes back to the sort of classic, if you're moving in a car that's travelling at the speed of light and you turn on the headlights, what happens? Well, everything is going to be travelling at the speed of light regardless of the motion of everything else. Next up, calculate the length of the spacecraft measured by the observer on Earth. So what we're actually looking for is to calculate the actual length observed, which is going to be one of these. And we need to use the gamma factor in order to calculate what happens, to what extent length contraction occurs. So we know that length is going to get smaller, and because we're moving it close to the speed of light, yeah, it's going to be quite significantly smaller. Gamma factor is 2.55. Therefore, if we're looking to calculate the length as observed on Earth, you're going to need to contract that, make it smaller by quite a significant amount. So you end up with an answer of 14 meters. Okay, there we go. I think key to that problem is just understanding it's moving fast, it's being observed, therefore length contraction is going to be apparent for the observer. Here's the next questions. And we have to show that under Galilean transformation, the rocket that is moving towards the spacecraft is going to appear as if it's traveling at 1.6 c, which as we know is impossible, but it's pretty simple. Galilean velocities are additive. So if you're walking at 2 meters a second and someone else is walking towards you at 2 meters per second, they would appear to be traveling at 4 meters per second towards you. So yeah, it's just a simple matter of adding them both together. However, if you want to calculate the actual speed of the rocket, we know it can't be traveling at that speed, so we need to use the Lorentz transformation for velocity. Now the key to answering this correctly is realizing they're moving in opposite direction. So one of these numbers is going to be negative. So I'm just going for the spacecraft. Why not? From there, punching in all our numbers, because it's both craft are traveling very, very fast. Remember that minus sign, okay, for the one of the values, doesn't matter which one. But you are going to end up with the object still traveling very, very fast. At least we've found out that it's no longer violating the speed of light. Mass cannot travel faster than the speed of light. or even at the speed of light. So therefore, which of your calculations is valid? Well, it's got to be B2, because you cannot travel greater than or equal at the speed of light if you have any mass at all. 0.99 is less than the speed of light, and the transformation assumes the speed of light is constant between reference frames. There's your answers.